So what is this topic of chain rule? What is this here? So first, let me give you the big picture. Given f and g, given functions f and g, if we know f prime and g prime, then we can find the following. First, we can find this f plus g and the prime. And then we can find what? We can find f minus g, and then we can find the growth f. So let me now have some space there. Yeah, so f minus g, we can have that. Now, so we can have then what else we have? Now we can have the f times g, then prime. We also have f over g. Write it this way. Yeah, also have f over g. So given two functions f and g, let's say if we know f prime and g prime, then we can find all of these. Then we can find all of these here. If we know f and g and we know their derivatives, then we can find the derivative of the sum. We can derivative of the product. You can find the derivative of the quotient. You can find this guy. And we have all these rules. Yeah, we know this one. F plus g prime, well, that's easy. What is that? That will be, what is it? That will be f prime plus g prime. This is equal to, this is simply equal to what? This is simply equal to f prime and then plus g prime. And then all the rules you know. And then we have the product rule, and then and then what? Yeah, and then we have the quotient. How about the product? What is the product rule? The product rule is equal to this right here. Is equal to, this is a regular product rule, f prime plus f prime g, and then plus, this is what? Plus the f, and then what? And then g prime. Maybe to clarify this, let me just put all of these guys in parentheses. This is a g prime, this, and then we have this, f times g prime. And then this is g, so let me write g here, g, and then this is what? G, f prime g. So that's the product. And the quotient rule, yeah, we know that. F prime g minus f g prime over g squared. Okay, so we know these rules. Now, given the two functions f and g, and then f and g and f prime and g prime, then we can find all of these derivatives. Now, what is the other way of combining the two functions? Given two functions, these are the ways you can combine. If you have two functions f and g, we can create a function called f plus g. We can also create a function called f minus g. We can also create a function called f times g. And then we can create a function called f over g. Now, the other way, the most important way of combining the two functions is actually this. Is actually what? Is actually this.
Little buddy?
Equal f of g of x is a composition. This is now the other way of finding of combining them somehow. Using the functions f and g as ingredients, how can you cook up more functions? And these are the functions we can cook up. Okay? So using a jam and bread, how many different kinds of food can you make? That's what we're talking about here. And then if f is jam and g is bread, then we can cook up a food. We can cook up a function called f plus g, f minus g, f times g, f over g, and then the most important of all functions of creating more functions is by composition. And so we get this. So now the question is, what is now the derivative? What is now the derivative of this? What is now the derivative of this right here? What is this? So if you know f prime and if you know g prime, can we get this? Can you get this guy? So you have f over g of x prime. So take the derivative of f of g of x with respect to x. If you do that, then can you actually find this guy? If you know f prime, if you know f prime and g prime, can you find this guy here? And the answer is yes. So we have a formula for this, and the formula is actually right here. That's what it is. In DDX notation, by the way, this DDX right here, this is called a Leibniz notation. This is it's called the Leibniz notation derivative. Leibniz notation of derivative. And this prime here, I just call that the prime notation. There's really no special name because we use it all the time. We just call this the prime notation. So if you're f of g of x, so if you have a composition of two functions, and we know the derivative separately, then this is how we can find the. That's what that is. In Leibniz notation, it looks like this. Kind of look like this. It does look like it's a little more complicated, or simply in Leibniz notation, if you can write like actually you can write it like this. In fact, this is the notation which many students are used to because it is actually the simplest. So we use this notation right here. We use this notation. This is called a chain rule in Leibniz notation. This is the chain rule in regular prime notation. They are the same thing. They're the same thing, but written in two different notations. And here's the partial proof. The full proof is slightly beyond this course, so cannot provide a full proof at this point. In fact, the full proof shows up in Calculus 3. So I don't know how many of you will be taking Calculus 3, but in Calc 3, you actually get to this guy. Full proof. But at least, you know what? Even if you don't have full proof, the partial proof, I still want you to study this. Look at this very carefully. And when you look at this proof here, I want you to be careful with this. Okay, when you study the proof here, there are two things which you have to be careful. I want you to distinguish these two. So distinguish this. Distinguish f of g of f of g of x plus h. Is it this? Or is it this? Or is it this? So you have to be very, very picky. So the two are kind of similar, but it's not that not similar. So is it f of g of x plus h? Or is it f of g of x plus h? Are they different? Yeah, they are different. So very, very different. Okay. So you have to be very careful. So studying the partial proof is actually very good exercise. So I want you to study the proof. Also, let me get to the derivative here. Now let me get to the definition of derivative again. What is the definition of f prime? See the definition of f prime. That is the definition of derivative. What is it exactly? The definition of derivative is this right here. So what is that? So let's look at f prime at x. F prime at x. F prime at x. What is this equal to? This is equal to, so we have different versions, of course. The different versions. So the different version is this one. The limit h approaching 0. So this is h. Then f of x plus h. F of x plus h and the minus f of x. What is the other version? The other version, the second popular version, is the other version, the P version. Or we can actually use any other letter, but the limit. So let me write f prime of x here again. F prime of x is equal to what? Is equal to the limit t approaching x. And then this is equal to what? Is equal to this f of t. Let me write this. Let me just type this in. Okay, type in this. So this is going to be, now the numerator is going to be f of t is going to be f of t minus f of x. Then over, this is the denominator now, t minus x. T minus x. Now, you will see these kind of definitions over again in this class. So this doesn't just show up here, it will also show up in later sections, in later chapters in our course. So when you look at this here, I want you to be very careful, and I want you to have a very strict understanding of what this is. In this case, what we do have is, you have to focus. Let me maybe mark this guy in, let's say, how about in green? How about if I make use, let's say, orange? Okay, let me use orange here. Let me use orange color. Note that this X here, is it orange? No, this is not orange. Orange. This X right here is the fixed point. Must, or you know what, let me make it a little bit different. So this X right here, this guy here, must match this guy and this guy. Once again, we are using the letter X here. So when you use the letter X, what does it mean? What it really means is that these guys, they don't have to be X. They can be W. They can be 2X. You don't need to tell me that. They must match. That's what it is. So I just color coded it here. This guy, X, X, and X, they must match. We need a triple match here, a triple match. Must match exactly. Otherwise, we cannot apply this definition formula. The definition, okay? So here, same thing. If you have an X here, then this X must match with these X's here. So in this case, we need to have a match here. So now let me, how about if I use a different color? Let me use green. And then now, H, this guy H here, and this H right here, and obviously has to be plus H here. This plus is actually part of the H. And then they must be exact match. Note that this H right here also must match. So you see, instead of X, H here, if you have 2X, yeah, it works. If you have 2X, that works too. So all it means that these X's must match, and the H's must match, exactly. And the same thing with this guy. If you have this right here, then how about if I change to blue? This X right here must match this X right here, and this X right here, and this X right here. Or in this case, you have 4 X's. These 4 X's, they must match exactly. That's what it means. Exactly. So can you replace X by W? Yeah, we can replace all the X's by W. We can replace all the X's by let's say K, or C, or even 2X. We can even replace it by sin X if you like. Sin X, yeah, we can apply. Well, actually, in this case, probably not, because it is actually we can. We can replace these X's by sin X, or even cosine X. So now here, why do I talk about this? Because of this eraser here. So now we want to show this. This is a partial proof now. The partial proof, how do you get this? So now we start with this guy right here. F of g of x, and that's fine. Now we have to understand what this guy is. What is the derivative of f of g of x? So in this case, f of g of x, that we can call it like f capital F of x. So in this case, what is capital F of x? We can think this way. So what we can think is this is now equal to capital F of x. We can, you know what? Let me change the graph. The capital F of x can be thought of, what? We can let that be small f. F of g of x. So if capital F of x is this right here, then what is f prime of x? Then what is what f prime of x? What is f prime of x? How do you write this? This is equal to what? This is equal to what? This is equal to capital F of x. Oops. This is equal to the limit. So write the limit here. So you know what? Let me write the limit over there on the next line. Okay, you know what? We'll just write over there. This is equal to the first step, limit of what? The limit of capital F of x plus h, even h version minus the what? Capital F of x, and then divide by h. Ah, this is not a good idea. So these two are completely separate. We put a wall here. Separate. And this is h of x, and we get this. Limit h is equal to 0. The question is, what is capital F of x plus h? What is this guy here? What is this guy right here? Let me ask you this. Is this f of x plus h? Is it this guy? Or is it this guy? Which one is it? Is it number 1? Or is it number 2? If f of x plus h, is it this guy number 2? Or is it number 1, this guy? Which one is it? Can you tell me, or can you distinguish?
Number 1.
Is capital F of x plus h equal to the first guy, or is it the second guy? Can you tell me which one it is, class?
First guy.
Can you tell me what it is?
Wouldn't it have to be 1?
Mm-hmm.
Yeah, that is number 1. You're right. If you look at this, you're exactly right. You see this guy right here. You see this guy. Okay. So anyway, you know what? I'm not going to continue with this proof here. But this proof is not easy to read. Okay. So, but I want to kind of look at it, and this will help you understanding the definition. But you know what? When students learn these definitions here, many students don't pay attention, and they don't care about these X's and the W's here. But what I'm letting you know is that when you use these kind of definitions, plus just like in other equations, you have to know which variable is matching with which variable. So here I color coded here X's and the H's. So if you want to use this definition, what has to happen? The X's and the H's, they must be exactly the same, exact match. We need an exact match. And this argument is not just what? It's not just from chapter 3. You know, when you get to chapter 5, let me see the chapter 5, no 3. And no, when you get to chapter 4, you are going to study. We are going to study this. We're going to study this. This is AX. Let me now show you what will happen in chapter 4. In chapter 4, we are going to have a formula. We'll get into a topic of integrals, and then we have f of t dt, and then this right here, and then this is ddx. I know this one here, you will not be able to understand what I'm writing here, because this is chapter 4. But I'm trying to teach you how you should read. So this right here, it turns out that this is equal to f of x. Again, this guy is also to chapter 4. This guy, let me just write it out. Obviously, it is not covering this section. This is what? In chapter 4. Chapter 4, this is going to be one of the formulas. Well, this we're going to see maybe in about 2 weeks. Maybe about 1.5 weeks, 2 weeks, we'll see this guy. So now, when you look at this here, you have to understand when you have this, what is exactly going on? Well, you have to look at the position of the x's. Okay, so what we have is, we have x here, we have x here, we have x here, oops. We have x here, and we have x here. We have x here, and we have x here, and we have x here. So, what do you think could happen? Do you think I can replace all these x's by x squared? Will that formula work? Yes, it works. If I replace all these x's by x squared, then it works. Can I replace all of these x's by 2x? Yeah, that works too. Or can I replace all these x's by w? Yeah, we can do that too. All it is saying is that this x and this x and that x, they're what? They're exactly the same guy. That's all it means. Not less, not more. So what it means is that these x's match. That's what it means. That's what it means. So if I give you what is, let's say this, what is, and then let's say I can ask you what is this, and then I can ask you here, I can ask you what is this? D of, you know what, this is now here, D of here. This is a logical, basically logical question. What is D of x squared? D of x squared. A D of x squared. And then times this, and then what? A x squared. Then we have f of t dt. So this is f of t dt. Let me type in f of t dt. So this is now f of t and then dt. And then if I ask you this here, do you think you can tell me what this guy is? Do you think you can tell me what the result should be? Okay. How about this? Let me write this. Another one here. How about this? How about this ddx? Yes. Then integral a to x squared. Then f of t dt. Okay. Now let me ask you. I have given you this formula. This is the formula right here. That's the formula. Okay? This is the formula. So you know what? This is the formula right here. That's the formula I'm giving you. That's the formula. Okay, in chapter 4, that's the formula. So here, that's the formula. Now, given that formula, do you think you can answer this question? Or do you think you can answer this question? Which one do you think you can find the answer? Can you answer number 1 or can you answer number 2? Which one can you answer? When you have that formula there, by having that formula, can you answer number 1 or can you answer number 2? Which question can you answer? That's my question. 2. Can you tell me which one you can answer? Number 1 or number 2?
2.
What?
2, because the x's match.
Oh, the
Yeah.
x is
You can answer number 2. See, if I give you this formula, then if I ask you number 2, you can answer it. But if I give you number 1, that one you cannot answer.
no, but why don't
You
I
can answer that one
Mm.
with this formula. With the formula given to you, you cannot answer number 1. You can answer number 2. So do you understand what I'm trying to get at? So you have to be very, very picky. So we have already seen this when we have the limit of sine x over x and the x approaching 0. X and the x and x, we each have a triple match here. So you have to remember, when you see the letter x, what does it mean? There's no mystery about x. It means that all the x's must be the same. And then here, not only x's must be the same, but also what? Also this guy right here, if you look at the formula here, also let me now write down, how about if I use green? This t right here, this guy should also match this guy as well. This is t. So if you put an x here instead of t, it doesn't work. They have to match. So instead of t, can I use z? Can I use k? Can I use c? Yes, you can. But they must match. Not only that match, but you also see this match. So now what other color can I use? I can use I can use blue. And blue, let me use a thick font. This function f right here, that's the function right here. This function must match this function right here. So you have to know exactly what has to match what. So I want you to learn how to understand these formulas. Do you understand what I'm saying? So students are not, they don't have this kind of training here. So initially you need some practice. You need some practice here. So I want you to read. So when you see the letter x, that means x's are the same. And all the t's are the same. And the f are the functions, they must be the same. F is not a function. But f should also match here as well. Same f and this is f. But although the inputs are different, this is f of t and this is f of x, they're not the same. But the function must be the same. Function must be the same function. So this is how things have to match exactly. So using this, or if the formula is given to you, then you can answer number 2. But answer number one, the question one, that one we cannot answer. Given this formula, number one cannot be answered. Again, given this formula, number two can be answered. Okay? So let me just wipe this out from these notes here. I'm sure that some of you will get mixed up here. So let me erase all of these integral stuff. This is chapter 4 stuff. It will show up very soon. I'm trying to help you how you look at these formulas from a logical standpoint of view. Okay? The substitution must be exact. Matching must be exact. There is no leeway. Okay, so now let's look at this. So here, what is this? Okay, let's look at example 1. So I'm going to do is I'm going to do the save one and then clear all this. So now let's look at example 1. I'm going to scroll this over. And now let's look at some problems here. Okay. So let me do a full screen here. Let's do it. Okay, example 1. Example 1, f of x equals sine of x squared. Now we want to find f prime of x. How do you do that? Now, if f of x is equal to sine x, if f of x equals to sine x, if x equals to sine x, then what is true? Then what is true is f prime of x is equal to what? Is equal to cosine x. So this is correct. Yeah, this is correct. Now let's look at this. So what happens if, let's say, you know what, how about if I call this guy, you know what, let me erase this guy. Let me call this guy G. I don't want to call by the same name. So let me call this guy function G. We just use the same color. If G of x equals x sine x, then G prime of x is equal to, or what is equal to, cosine x. Now the question is this. If f of x is equal to, what? Sine of x squared. If f of x equals sine of x squared, this right here, then do you think f prime of x is equal to cosine? Do you think f prime of x is equal to cosine of x squared? Do you think this is right? Question is this correct? It's correct? What do you think?
No, it is not valid.
It is not valid, you're right. Now let me tell you the formula. The formula in Leibniz notation is actually this. EDF, if you write the derivative notation here, ED of x, we put this in parentheses, and then what is the derivative here? The derivative, the function is sine x. So let me write sine of x, and then if you take the derivative of this guy, what is it equal to? This is actually equal to cosine x. So now what I'm going to do is I'm going to write this in red. X here, X here, X here. These x's must match. But now, how about if I give you a problem like this? How about now the problem is this? Now what we have is e dx. Now here what we have, what I'm going to do is now this e dx, e is blue. So let's see, how about if you have this? If you have d of dx, then now we have what? Sine of x squared. Now what we have is we have the function is sine x squared, and now we're going to take the derivative of that with respect to x, not with respect to x squared. And therefore, can you answer this question here? Now this one involves chain rule. This involves chain rule. This is not a regular derivative. But if I ask you this, let's say if I put a square here, and a square here, then will this equal square here? Will this be correct? Will that be correct? If I give you this problem right here, where I put x squared, then the derivative of sine of x squared with respect to x squared is equal to cosine x squared. Will that be correct? Yes, it will. That will be correct. But that is not what we have. What we have right now in example 1 is this guy right here. This is what we have. We have sine of x squared, and we now want to take the derivative with respect to x. So that's why it is not straightforward. So this one here, this is for the question mark. Is it correct? And the question is no, incorrect. This guy is therefore incorrect. So do not make this mistake. Or the incorrect, there will be 2 R's, so incorrect. Okay, so now let's try to figure out what's going on here. So I'm going to do this example 1 in different notations here. Well, I'm going to save this guy, clear all this guy. I'm going to do this in a different notation. Let's look at first the regular prime notation. So first of all, this f of x can be written as what? Can be written as f of x is equal to what? Can be equal to f of x can be written as sine of x. Yeah, sine of can be written as what? How about f? G. How about g? This is sine of what? Sine of x squared. Sine of g of x. H of x. You know what? Let me see. Am I confusing? You know what? Let me write it this way. How about this? Let me just clarify this. I think it's easier if I just write out the function. So let's say, how about f of x? So write this in black. In this case, f of x can be written as g of h of x. What is g and what is h of x in this case? Where? In this case, where? What is g of x? Where? Where? What g of x? So g of x is equal to what? G of x is equal to sine x. And h of x is equal to x squared. So does that make sense? Get this. If f of x equals g of h of x, then we can say g of x is sine x and h of x is x squared. If you combine them, if you now find g of h of x, then that will be g of x squared. So that would be this. So then what is f prime of x? What is f prime? Now from here, you can figure out what is g prime of x. From here, let me first get these values here. Why don't we take the derivative here first? So if you do that, so what do we get? So what we get is from here. What we get is g prime of x. G prime of x is equal to g of x, and that would be cosine x. And h prime of x would equal 2x. So then what is f prime of x? F prime of x is going to be now f plus g prime. This is now going to be g prime. This is going to be what? F prime of x is going to be g prime of h of x. And then times, this is h prime of x. That's what the chain rule is. This is the chain rule. So what is that? So what is now g prime of h of x? What is g prime of h of x? Now g prime of x is cosine x. What is g prime of h of x? A g prime of x is h of x is now going to be cosine of h of x. And h of x is actually what? What is h of x? Oh yeah, h of x in this case is actually x squared. You know what? Should I write this in 2 steps or 1 step? Okay, let me just write h of x. I'll write this in 2 steps. And then times h prime of x, which is 2x. Okay, so what is that equal to? This is equal to now, what? Let me just go this way. Go straight. So this is now going to be what? This is now going to be is equal to cosine of x squared, and then times what? Times 2x. we can actually write the 2x in front of it. So the final answer comes out to be this right here. So usually we write this answer, we write the 2x front because 2x is a little bit simpler. So we generally want to write the answer this way. This is equal to 2x times and then what? Times cosine of x squared. Usually this is how we write it. This is called the chain rule. Now how about if you write it? How about let's look at number 2. Number 2 in this case, g of x equals sine square of x. So this is sine of x squared. So in this case, what is the leading function? The leading function is what? Is square. That's the leading function. So let's say, how about this? In this case, f of x, you can say that this is equal to g of h of x. Excuse me. So this is going to be this, where g of x is going to be what? Is equal to x squared. And h of x is equal, what is h of x? H of x is equal to sine x. We get this. So now how do you do this now? Y h of x, so in the h of x, so now what is g prime of x? G, you know what, sorry, they call it g here now. I messed up. You know what, I think I need to rewrite this again. We don't know that we call it g there. So how about this? Let me rewrite this here. Now in this case, how about this? Let g of x equal to h and hi. How about a j of x? We let g be h compound j, and so where h of x is the leading function must be the square function. And then j of x is equal to sine x. You get this. So now we have written that original function as a composition of two functions. Now we do know the derivative of x squared, and we also know the derivative of sine x. So from here, you can find the derivative. What is the derivative? The derivative is going to be this. It's going to be what? H prime of x. H prime of x is equal to 2x. And what is j prime of x? J prime of x, that will be cosine x. And so what is g prime of x? G prime of x is equal to the this is going to be h compound j of x. So that will be h prime of j of x. Then times what? J prime of x. Get this. So what is that? That was h prime of x is 2x. So what is h prime of j of x? That would be 2 times j of x. 2 times j of x. And then times what? Times j prime of x, which is cosine x. So what is j of x? J of x is sine x. So that would be 2 times sine x times cosine x. And if you will, that is actually equal to what is equal to let me put this in parentheses here. It's actually equal to sine 2x if you like. But that double angle formula for sine is not required. Okay? If you don't know that rule, that's okay. So this is not this is not the course in trigonometry. So if you give me that, so the final answer will be this right here. The final answer will be this right here. If you give me the final answer in this form, in sine 2x, that's okay. I will accept that as well. Okay.
Just a question: why does h of x equal x to the power of 2 when the x is just without any powers?
What is it?
Why is h of x? Why is the h of x considered x to the power of 2?
Because g of x is sine square x. So basically, g of x in this case is equal to sine square of x, and sine square of x really means sine x and then the whole thing squared. That's what it really means. This whole thing squared. That's what it is. So what does this function g do? If you have an x here, then you apply the sign, and then we square. So the last thing we do, that is actually the outer function. So in this case, if h of x equals x squared, and j of x equals sine x, then from here on, what is h of j of x? Do you think you can evaluate this guy? If h is x squared, h of x is x squared, and j of x is sine x, what is going to be h of j of x? Can you figure what this is? If h of x is x squared, and j of x is sine x, what do you think is h of j of x? And that will be sine of x squared. Does that make sense? And that is exactly what we have right here. G of x is this guy right here. So G of x is actually what? Same as h of j of x. Oh, by the way, this j right here must be a small j. Sorry. This must be a small j, not a capital J. There is no capital J here, small j. Yeah. So anyway, this is clear? So G of x equals sine square x, but there's no way to find the derivative of sine square x directly. So we write this G of x as a composition. So note that G of x is h of j of x, where h of x is x squared, and j of x is sine x. So when you combine h of j of x, and take the composition, then h of j of x turns out to be sine of x squared, which is exactly what our G is. So the first step is writing this function as a composition of two functions. So does that make sense? Yes or no?
Yes.
Okay, now what I'm going to do is this. I'm going to save the screen here. And this time I'm going to do example 1 and 2 again. This time I'm going to use a different notation. I'm going to use this notation, which is going to be much easier. So this notation is much easier. Many of you will have an easier time if you use this notation. So now let me use the right notation in this case. So what I'm going to do is this. I am going to write y. I'm going to write y here. I'm going to write right this. I'm going to y is equal to, and the y is equal to, and then this is equal to sine of x squared. X squared. I'm going to do this. So first, let me write sine of x squared. Y is equal to sine of x. So I'm basically letting the def of x be y, and then I'm going to write sine of x squared. Now, what is sine of x squared? Sine of x squared, I'm going to write this as sine of w. Not win, sine. Win, sine of w. And I'm going to let this w is equal to x squared. So what we have is f of x, I'm going to let that be y. And then y is equal to sine x squared. And sine of x squared, let's write this as sine of w. And w is equal to x squared. Okay, now what is this? Then f prime, now we have to figure out f prime. And this f prime will actually be the same as dy dx. Now the question is, what is the chain rule in this Leibniz notation? It is actually going to be this. dy over dx is actually dy over dw. And then this is equal to dw, and this times dw over dx. So is dy over dx equal to dy over dw times dw over dx? Yes, that is what we call the chain rule. Even though this is not something we prove, but that is what we call the chain rule. So as you look at this, why do we call this chain rule? Because when I mark this dw dx like this, these dw and then let's say put it, and then they're the same here. It kind of looks like a chain. Especially not just a 2 chain, but if you have this is a 2-piece chain, but we can have a 3-piece chain, 4-piece chain, 5-piece chain, and so the chain can get longer, and that's why it kind of looks like a chain. That's why we call this a chain rule. So dy over dx, is that equal to dy over dw times dw over dx? Yes, it is. Now, is dy over dx a fraction? Is this guy a fraction? This is not really a fraction. It's not really a fraction. This is dy over dx is really d dx of y. All it means that it is the derivative of y with respect to x. It's not really dy over dx, but it's dy over dx. It's not a fraction, but it behaves like a fraction. And that's why we like to write this in fraction notation. Again, this guy is not a fraction exactly, but it behaves like a fraction. And so you also have a rule such as this, like dy. Another rule you will see is that dy over dt, like dy over dx, is equal to. By the way, you are going to see this about 2 sections later. You will see that this is actually equal to dy over dt. So let me write this rule because you will need this rule. And then dx over dt. So when you treat this dy over dx like a fraction, yeah, it's not hard to understand. And then we also have another rule like this. Dy over dx happens to be the same as 1 over dx over dy. So once again, this dy over dx is not exactly a fraction, but if it's not a fraction, why do we use a fractional notation like this? And that is because it behaves like a fraction. It's not really a fraction. So dy dx is not really dy over dx. It's not that. It's actually ddx of y. But we write this as dy dx, and we write this in a fraction notation. Why? Because it kind of behaves like a fraction. So that's the chain rule. All of these are also chain rule too. Okay, so now, once we write that, then now what is next? The next is kind of easy. Let's look at this here. Now, what is dy? What is dy dw? What is dy dw? Now, dy dw means, or dy dw, dy, y is equal to sine w. You see that? So what we have is y is equal to sine w. So let me write this down. So in this case, what is the relationship between y and w? So the relationship between y and w is y is equal to what? Y is equal to, or y is equal to sine w. Or what is y equal to sine w? So now what is now dy dw? What is dy dw? This is equal to now dy over dw. So dy, oops, y, dy dw. What is the derivative of y with respect to w? And that will be exactly cosine w. Thus, ddw or sine w. What is sine w, ddw of sine w? Now, of course, that will be cosine w. This one not a problem because when you had ddx of sine x, that was sine x. That was cosine x. The ddx of sine x, what was that? d of sine x was cosine x. They have a match. In this case, we have a match. Yep, we have a match. In our case, we have a match with w. This guy is exactly the same as this guy. So right now, we have a match here, w. We take the derivative of the w, now we get cosine w. So dy dw becomes cosine w. So this guy is cosine w. So let me write cosine w. And then times dw dx. What is dw dx? So that's 2x. So now what is that equal to? So what is that equal to now? That is equal to, we can write the 2x in front of it, and then we can write cosine w. So what is w? W is x squared. So we can write x squared. And so now the final answer looks like this. The final answer, by the way, must be in x, must be in the original variable. So cannot keep the w there. The final answer comes up with this like it. This is probably the easiest way you can follow. Kano in Leibniz notation. How about, let's say, example 2? What is example 2? Example 2, what is this? Example 2. Okay, example 2, what is here? What is in this case? What's that? Okay, so let's look at that here. Example 2, what we have is y is equal to what? Y is equal to? Well, y is equal to q of x. Y is equal to q of x. So y is equal to what? Q of x. So this is not y is equal to q of x. Y is equal to q of x. So what is q of x? Q of x is sine square of x. So this one, why don't we call this guy? You know what? Q of x is sine square of x. So this is sine of x squared. So let me write sine of x squared. And now this one, we can call this guy W. We can call this guy, how about V squared? Then what's V?
I can
V
do
is
it.
equal to now sine x.
Do you have time?
We can say this. So what is now G prime of x then? G prime of x, this is basically dy dx. Now what is dy dx? The dy dx, this is actually equal to dy dv. And then times dv dx. Now the question is, what is dy dv? Y is equal to v squared. So this guy is 2v. And then times dv dx, v is equal to cosine x. So what is dv dx? That would be cosine x. So we actually get cosine of x. And all you have to do is what? Replace this v by sine x. So this turns out to be, so let me put a bar here. This is equal to 2 times sine x cosine x. So this is equal to 2, or what? This is 2 sine x, then cosine x. Okay. That's what I'm going to do is now this time, let me do this one more time. Yeah, it's almost time for a break, but I know we have past break time. But now let me do this example one more time. One more time. Third time. Okay, third time. Now, when you look at this formula, when you look at this function, when you look at this number one, f of x equals x sine square x. Now, note that the leading function is sine. This is f of x equals sine of x squared. It is sine of something. That's what I call the leading function. So now, what is f prime of x? F prime of x is now going to be the derivative of sine. Now, what is the derivative of sine? The derivative of sine is cosine. So it is going to be cosine of something. Now, in this case, do we have cosine x? No, we don't have cosine x. What we really have is cosine x squared. So we put this. So once again, f is equal to cosine of something, so sine of something. The derivative of sine is cosine, so we have cosine something, but not x, so now we have x squared. Now, this expression right here, we don't have x, we have x squared. So now what we do is now we take the derivative of that variable, that expression, which we treated like a single letter. So therefore, the derivative of that x squared is now going to be 2x. And this is now the final answer. Now let's do example 2. This g of x is sine square of x. This is equal to something squared. So in this case, the leading function is the square function. So this is g of x is like x squared. So what is g prime of x? G prime of x, this is like g of x is like x squared, something squared like x squared. But what is the derivative of x squared? The derivative of x squared is now 2x. But in this case, we don't have x. We actually have sine x. So we have sine x. So this sine x is that which we treat like a single letter. So we have sine x. Now what do we do? Now times the expression which we treat like a single letter, we now take the derivative of that, which is now cosine x. So the answer is this right here. Okay, so let's take a break here. Let's take a break. A 10-minute break. Yeah, we'll take 10-minute break, and then we'll continue at what? It's already 9:57. So let's start at 10:07. Okay. So let's start at 10:07. Well, we'll have a 10-minute break. We'll be back. I'll be back in 10 minutes.
You sure you don't need to go?
Yeah, would you? It'd be great.
Okay. Where is
I
it?
can run.